So with our complex numbers, we have this idea of their value, often called an absolute value, or occasionally you'll see the fancy word modulus. And this is just trying to get an idea of the overall magnitude of that absolute value of that complex number. So if you take a look at the diagram here on the right, this is going to look, pretty familiar. When we were going from rectangular to polar coordinates in the past, we found that same value using the Pythagorean theorem. Note that z is often the letter used to represent a complex number instead of x's and y's. So frequently the notation that's used to talk about its absolute value or its modulus is z in those brackets. Those brackets are absolute value brackets. The notation here is a bit funky, but what we're really doing is just finding the square root of a squared, the real part, plus b squared, the imaginary part. Hopefully that looks very familiar. It's just our Pythagorean theorem. It's exactly what we did in the previous set of videos when converting from rectangular to polar coordinates. So again, we've got that little right triangle. It would probably be helpful if the colors were consistent. We've got that little right triangle that we can create in the rectangular plane. And we can use Pythagorean theorem to find the hypotenuse. And again, that hypotenuse is going to get the special name absolute value or modulus. So as far as the work that needs to be done here, it's not much. Our a value in this case is 8, so I'm going to square it. Our b value in this case is 6, so I'm going to square it. 8 squared is 64, 6 squared is 36. So that's going to be a 64 plus 36, which is 100, but the square root of 100 is just 10. Jumping to one that's a little tricky, -3 minus I. Again, keep in mind our a value is the real part, so the real part is -3. When I jump over to that b, I is not included in that b value, so this is just a -1 quantity squared. We don't want to include that I in there. We don't want to accidentally square that I. Squaring I adds another -1 into the mix. We don't need that. So this would be a -3 squared, that's a 9. -1 squared is a 1, so that becomes a root 10. Unfortunately, can't do anything with root 10. It does not break down, so that's just going to remain a root 10. Last but not least, taking a look at number 9. Number 9 here, our real part is 2. So it's a 2 squared. And then our imaginary part, -11. So we have 2 squared, which is 4. -11 squared is 121. Putting those together gets us root 125. Now that one we can reduce. 125 is the same thing as 25 times 5. The square root of 25 is 5. And there's a root 5 left behind. So again, the idea here is in order to find that absolute value or that modulus, it's the same as finding R, and that might be worth writing down. Same as finding R when going from rectangular to polar. So we just did this work finding our modulus, our R value. We're going to also do a bit of work to find our theta value. So eventually the goal is to go from rectangular versions of complex numbers into polar versions of complex numbers. That's our ultimate goal here.